Hello everyone. In this video, let us try to look into one more problems of crosstalk coupling capacitance. So for example, the input of the victim driver is held at constant logic 0. As a result of that, the output of the inverter will be held at constant logic 1. So we had taken this analogy of bucket with water. So let's when we say this is logic 1, it means that the buckets over here are completely filled with water, and they won't be emptied unless and until the input of the victim driver goes to logic 1. So when it moves from logic 0 to logic 1, this tab gets open, and all your buckets over here will get the water in the buckets will get drained out through this tap. So unless and until that happens, it should stay at logic 1. But what happened, this doesn't switches, but there is a nearby aggressor that tries to switch from logic 0 to logic 1. So this tap is closed, but we have a nearby tab that is open. Okay, and there is a coupling capacitance, or there is a coupling which is happening between this particular net and this particular net. So in this case, assume that this particular coupling capacitance is a bucket which is placed in a reverse order, and there is a hole which is present over here now. So this particular buckets which are supposed to get drained out through this inverter, they are not getting drained out through this inverter, but they will be getting drained out through this particular inverter. So what happens? So something like this. So this is the flow of water, or this is the flow of charge that will happen. So the charges which are or the water which is there, which is completely filled in this particular buckets, they'll try to go through this leaky bucket which is placed in the reverse order, and this tap, since this tap is open, and so what happens is this particular, some of the water from this particular buckets tries to get emptied out from here. So what happens, because of that, you see a dip in the water level inside in the charge, or the dip in the water level in the bucket. So because of this, now there should be someone who should fill up this dip, or if this dip goes beyond certain threshold, then it will be completely emptied, and if it is completely emptied, it will take time for that buckets to get filled logically. So what happens, since this tap is now open from the direction where you can fill this, from the direction where your PMOS is on, so there is a small tab which is open over, which is already open over here, which is the PMOS tab, and it can fill up, it can restore the charges from the PMOS which is present over here. So basically these buckets can get filled up again by the PMOS which is open over here. But if the bucket remains, if the bucket remains empty for a long period of time, it might not happen, and it might stay at the bottom, it might stay emptied as well. So we'll be looking into all these problems of crosstalk in the crosstalk section. For now, we are looking into this dip, and what can this dip and what can go wrong because of this dip. So what can go wrong because of this dip? So let's say this particular dip passes through this inverter, and you get a dip which is like which is going from logic 0 to logic 1. You get that kind of dip, and again, let us assume that there is this particular net is connected to the clock pin of the flop. So flop has got a property that you should launch data. Let's say this is a rising edge flop, and you should launch data. It is supposed to launch data at the rising edges of the flops. Okay, so now what happens? It will be this flop will be launching data at this rising edge. It will be launching data at this rising edge. What it is supposed to do. But because of this particular glitch that it is seeing at the input of the victim, at the input of the victim net, this particular thing gets at the output also, and let's say somewhere where the net was constant, it sees a glitch over here, it sees an edge over here. So once this particular flop sees a small edge over here, it will try to launch data at this particular edge, and that is basically an incorrect data, because data is trying to get stable between this edge and this edge. So it is very likely that the data is unstable in this point of time, and it might launch an incorrect data because of this edge that it sees at the when it is supposed to stay at logic 0. It is seeing an edge and it is trying to launch the data. So the data might not be accurate, or data might not be correct at this point of time, and the flip-flop is trying to launch that data. So this is the thing that can possibly go wrong if you have a glitch at the input and that gets propagated through the inverter. But again, if there are things that we need to look into, that whether when this glitch gets propagated through this inverter, whether the magnitude of the glitch remains the same, or it is a bit less, or it can even fade out. So there are so it depends on the property of the glitch. It depends on the height and the width of the glitch. So we need to look into all those, but that we will be covering in a separate class of videos that will talk only about crosstalk and signal integrity. So we will be covering that part over there. For now, so this was this is again one of the quality checks that we need to do for the clock tree also, and the best possible solution is to shield it. So that is one of the solutions, to shield it, and there are other ways how to control this particular thing, but this is again a check that we need to do. So we are done with all the quality checks parameters. So let us try to bring all of them in a single frame, where we say that let's create a checklist for us. So this checklist will be helpful for us whenever we build a new algorithm. Whenever we build a tree with a new algorithm, we'll be using this particular checklist to fill up and see what happens, and where are we on the algorithm? Are we good? Are we bad? Or whatever. Let us try to use this particular checklist as to quantify the H tree or to quantify the tree that we will be building. So the first check was the skew, which was the difference in the clock latency in the launch path and the capture path. Next was the pulse width. This was basically a check where we used to check that whether the high pulse and the low pulse are exactly the same as expected from the input. Next is the duty cycle, which is again related to pulse width. So we check whether the duty cycle that was sent at the input, before either it could be 50% duty cycle, or it could be 30-70% duty cycle, whether whatever is sent at the input, it does that remain same at the clock endpoint. So that is one of the checks. The next check is the latency, where we related the latency, and we talked some advantages about latency and why we should be having low latency and so on. Next was the clock tree power, which was again a function of clock tree, which is again a function of latency. So latency and power are very much related to each other. And finally we checked at the signal integrity and the crosstalk section. So starting from here, in the next video we'll be looking into one of the very important algorithms, or one of the basic algorithms, which will help us to clear a lot of our doubts, and that is the H tree algorithm. It's a very simple and it's a very basic algorithm, but being it a very basic algorithm, this will help to solve a lot of our doubts, lot of our concepts regarding to advanced clock tree. So in this section we'll be taking like only 16 clock endpoints, and try to build a small tree and see what are the and fill up the checklist and see what are the problems that are associated with that small tree, and how can that lead to bigger concepts. So let us try to look all this in the next video. Thank you.